we have. And one of those homologous series we had was alkanes, and we had started looking at the different alkanes we have and their physical properties. And I remember we left off when we had started on the boiling point and melting point. Okay, so I'll start from this graph here. So we said two of the physical properties that we have with alkanes, we have the melting point and then the boiling point. So like I said last time, when we are looking at the boiling and melting point, you notice that as the number of carbon atoms increase, the higher the boiling and melting point. Like you can notice here, we have one carbon atom, two carbon atoms, three up to 16 carbon atoms. So as the carbon atoms increase in the alkane chain, realize that also the melting and boiling point also do what? Increase. And like you can see on the scale, they're telling us the blue is standing for the melting point, while the red is representing the boiling point. So you realize that the melting point is a bit lower than the what? And the boiling point. Because remember, as you heat these different alkanes, you notice that I gave an example, like, for example, if you're to boil a glass of water and then a jerrycan of water, you realize that the one with a glass of water, their water will boil faster than the one using a whole jerrycan. So a whole jerrycan may take a bit of a longer time than than the what? Than the one with little water. But they almost have the same, they actually have the same boiling point because water has a boiling point of 100. But just imagine maybe you're boiling the water and then which other, maybe beans. Realize that beans will take a longer time than water. So at that rate, that is what we use to correlate the carbon atoms. If the carbon atoms are more, that means the boiling point will what? Will be higher. But then you realize that if we have 16 carbon atoms, there is going to be some sort of branching. You won't have like a straight chain, like maybe when we say propane, you realize that propane is straight all through with its hydrogen atoms here. But when you are looking at the one of 16, you may find that some of them are joined here, some of them are joined here. So at that point, when there is branching of that chain, to also take a shorter period of time because realize that the carbon atoms are closer to each other and they can easily be broken. So I don't know if we can understand that concept behind there. Juliet, if it's your first time, like I said, we can't go back for a lesson that took 2 hours. So you will need to go and watch the video we watched first. You will have to first go back to the video recorded in the first lesson, and then you will understand what we are talking about. Otherwise, we can't go back for that whole lesson. Someone is saying I'm too low. Try to increase the volume of your phone because it feels like I am shouting. Okay, are you now able to hear me? Okay, thank you. So, like I was saying, those that are joining us for the first time, kindly just follow us where we are and then go back and watch the video that was posted on the group. You can inbox Mr. Kaziba to share with you the link, and then you're able to watch that video. At least I'm seeing more yeses of people who are hearing me than those who ain't hearing me. So maybe you should check your device and then log in again. Um, okay, so I was still saying, when you're looking at the carbon chain, basically, you just need to understand that if the chain is longer, to have a higher boiling point. If the chain is shorter, you need a low boiling point and low melting point. So can we get someone to read for us the content that is on the next slide that I'm going to show? Yes, Wandera. We had discussed all this. We are just doing a review of what had actually happened in the previous lesson before we move to the next to the next physical properties. Wandera, you can go ahead and read.
Okay, madam, I'm not getting what's on the screen. Questions? Hello, madam. Okay. Can I read the first one?
Can you read the question and then its answer? Because we had looked at that. We are just doing a recap.
How do melting and boiling points of alkanes vary with the number of carbon atoms? We said an increase in the number of carbon atoms leads to increase in the melting and boiling points, which says melting and boiling points increase with increase in molecular mass since the Van Dyke's forces increase. Identify and explain other physical properties of alkanes.
Okay, sorry, just a minute. Okay, you can now continue. Okay, so like I was saying, when you're looking at how do melting and boiling points vary with the number of carbon atoms, we say that the melting point increases with increase in molecular mass since the van der Waals forces increase. So like I said, when the carbon chain increases, you realize that the molecular mass will also increase. Like for example, we said, who remembers the name of the alkane that has two carbon atoms? You can post in the chat or you raise your hand and tell us. Yes, Patricia.
Ethane.
Okay, ethane. So we say ethane has two carbon atoms. So when we are looking at ethane, you have two carbon atoms. And we say to be complete, it must have 4 bonds. That means you'll have a hydrogen there, a hydrogen here, a hydrogen here, a hydrogen here, and then a hydrogen here. And then this is ethane. Then what is the name of the alkane that has three carbon atoms? Who remembers?
Propane.
Propane. Not propane, but propane. Thank you. So we have propane. It has three carbon atoms. So that means we'll have hydrogen and hydrogen, then hydrogen this side, hydrogen this side. So you're going to look at your periodic table and you tell me the atomic mass of carbon. For those that can access the periodic table. Ngabira, I don't know how to help you because if the rest are hearing me, then I don't know how to help. Ngabiri and Rebecca, I really don't know what to do for you because if the rest can hear me, then I can't really raise my voice higher than it is right now. Okay, Hannah, thank you. It is 12. Some people I know are giving me the what? The atomic number. I asked for the atomic mass. So the RMM of carbon is 12. And then for hydrogen, what is the atomic mass for hydrogen? Sheila, just follow through. We have also just started. Thank you, Infinix. We have 1. So the atomic mass of carbon is 12, while the atomic mass of hydrogen is 1. And I'm sure every one of us at least looked at the periodic table. So in this case, if we are finding the molecular mass, that means we are finding for the whole compound. So for the whole compound, if we are looking at ethane, we are going to have a molecular mass of ethane. I'm going to rub off the structures. I hope at least you've taken note of the structures. So the molecular mass of ethane, which is it's going to be for ethane, we said it has 2 carbon atoms and 6 hydrogen atoms. So that means we'll get the atomic mass of carbon, which is 12 times 2, plus the atomic mass of hydrogen, which is 1 times 6. What is 12 times 2?
24.
24, good. And then what is 1 times 6?
6.
So when we add them, what does it give us?
30.
30, very good. So that means the RMM of propane is what? Sorry, of ethane is 30. So this is the molecular mass. That is how much it weighs. And then when we go to propane, we know that propane has 3 carbons. So that means RMM is going to be 12 times 3 plus 1 times the number of hydrogen atoms. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 of them. So what is 12 times 3?
36.
36, very good. Plus 8, what does it give us?
44.
44, good. So you realize that propane is heavier than ethane. Someone is asking what is RMM? RMM is the same as relative molecular mass. And like I've said, molecular mass is how much that compound weighs. And of course, you'll look at that in more details when you get to the next topic, which will be mole concept. But for now, you need to focus on knowing how much weight each of those ones has. So ethane is 30, then propane is 44. So after noticing that, you realize that propane will have a higher boiling point or melting point than what? Than ethane because of their variances in weight. Yes, Mariam. Mariam, you can unmute and submit whatever you want to say. Patricia, did you stop people from unmuting themselves?
No, teacher. I didn't.
Yes, teacher.
Teacher.
Please, Please talk. We are hearing you.
I can't hear you very well.
I don't know how many people are hearing me, surely. Just saying that chat you're hearing me, because I don't know what to do for people who are not hearing me. I really don't know what to do for you. Okay, so you may need to first log off and then come back. Really, I don't know how to help you, but at least I can feel myself. I am screaming entirely. Yes, Daniela.
Madam, I joined a bit late, so I'm confused about what we are learning. I'm requesting for you to explain again.
If we keep going back, will we cover anything? Okay, were you around in the previous lesson? Let's maybe begin from there. Were you around in the previous lesson? Miranda? Miranda, you can unmute and talk, okay?
Madam, what's the SI unit of the RMM?
It has no units because it's a relative mass.
Okay, madam.
Okay, so please don't concentrate a lot on this. I was just bringing it in just to explain the statement that was on the screen. To show you that propane weighs more than what? Than ethane. So don't focus all your energies here. Okay, so moving on to the next. So we said melting point and boiling point increase with increase in molecular mass. Says the van der Waals forces also what? Increase. And like I said, as the molecular mass increases, that means the forces holding those molecules also do what? Increase, because the number of atoms in those different chains have also what? Increased. So you'll expect the forces holding those molecules together to also increase. So the forces we find in those alkanes are the van der Waals forces. That one you need to have it at the back of your mind. Okay, so then we also identified other physical properties of alkanes, and we said alkanes are colorless and they are odorless. And then also something you need to note is alkanes having 1 to 4 carbon atoms are gases. So that means the first 4 alkanes are gases. Who can remind us the first 4 alkanes that we looked at? Yes, Saint?
You have methane, propane, and butane.
Okay, very good. So we have methane, ethane, propane, and then butane. Those are the first 4 alkanes that we have. So that means all those 4 are what? Are gases. Then from 5 to 17 carbon atoms, they are liquids. And then from 18 and above, they are all solids. Wandera, your hand is up. Okay, then we also said alkanes are insoluble in water and soluble in organic solvents such as benzene. Benzene, I'll not dwell so much on it, but benzene is also an organic compound. So in this case, we say that alkanes are insoluble in water because you realize that water is an inorganic component. So that means an organic component may not dissolve in the what? In the organic solvent. So that is why you find that alkane is soluble in organic solvents like benzene rather than water, which is an organic component. And then density increases with increase in molecular mass, but branching reduces that trend. Like I say, when you're looking at, uh, for example, when you're looking at a small stone, when you cast it into the water, it will sink into the water. But when you're looking at, at a bigger stone, if you're looking at a bigger stone, it will sink in water. But when you're looking at a piece of wood, you realize that it will only float on what? On water. So when you look at the weight of those two things, you realize that the stone is heavier than the what? Than the wood. So it's the same thing with alkanes. When the alkane is smaller, maybe it's thin, it has a less density than decane, which has 10 carbon atoms. So that means in that case, you'll have what? An increase in that density because of the increase in the molecular mass. And like you can hear the word mass, that means it's dealing with the weight of that given compound. So basically those are some of the physical properties that we have in in alkanes. Are we all together up to that point?
Yeah.
Okay, thank you. And please, after covering these things, please go back and read them. Otherwise, they may seem complex, yet they are the easiest part that you'll ever have. Okay, so this diagram was just showing the different melting points and boiling points of the different alkanes that we have. For example, when you look at methane, methane has one carbon atom, so you can see its melting and boiling points. They are way low. And then when you look at ethane, it has two carbon atoms. Still the same thing is happening. Then propane, butane, as the chain goes on increasing, you realize that the boiling point also goes on what? Increasing. And I know most all of us are mathematicians. The bigger the negative value, the smaller it is. And the smaller the negative value, the bigger it is. So that is why you realize that negative 30 is way higher than negative 183. So you notice that decane has a higher melting point than methane, and decane has a higher boiling point than methane. Those are some of the few things you need to take note of. Someone is asking what is van der Waals forces. I say those are the forces that we find in alkanes. They hold nonmetals together. Like for example, you see carbon and hydrogen, they're both nonmetals. So for them to be held together in a structure that you see, it's because of those van der Waals forces. Okay, so that's asking the first four alkanes. We looked at that in the last lesson, and we said methane is the first, ethane is the second, propane is the third, butane is the fourth, pentane is the fifth, hexane is the sixth, and then heptane the seventh, and this one you can also call it septane. And then octane is the eighth, nonane is the ninth, and then decane is the 10th. So you realize that from pentane to decane, we choose the polygonal names. For those that were there, we say that a five-sided figure is a pentagon. That means we remove the argon and we take the pent. And because we are looking at alkanes, and we said alkanes have a suffix of ane, that is why you have pentane here. And then hexane, you look at a hexagon, you remove the argon, and then you come and add the suffix of ane. So it's like that up to when you get to the 10th polygon. Okay, I hope at least we are helping even those that weren't around to get somewhere. Okay, so we move on to the next part. Please, those who are just coming in, I said if you didn't attend the previous lesson, we can't redo it. Go back and watch the YouTube video that was posted by Mr. Kaziba. And if you can't access it on the WhatsApp group, kindly inbox him to resend it. so that you can get along with us, because otherwise we can't repeat a 2 hours lesson. So go back, watch that video after this lesson. Just follow through for now, understand what you can understand, then go back and watch it. The name of the topic is carbon in life. Yes, it's the first topic in senior 3. So go back and please watch that video. So we also have the chemical properties of different alkanes. Yes, Saint?
Okay, teacher, sorry to take you back, but slight issues on the formula, which was the formula on the table. Is it that the CH should always be attached to, or it should always be attached to the number H, the formula?
I don't know if I'm the one who is not getting you well. You're breaking. I can't hear you well.
My issue is on the table, the previous table which you displayed, the section formula, the formulas, how they have been written. Is it that the C should go with the H? Because me here I have different ones.
Now remember, when we're writing
Yes.
those different, when we're looking at the different alkanes, we say the carbon is bonded to hydrogen atoms, right?
Yes.
So that means the hydrogen atoms bonded to that carbon will move with that carbon. For example, here we have 1 carbon, so it's bonded to 4 hydrogen what? Atoms. Are you seeing that? So it will move with its hydrogens. Yes. Then when we go to ethane, ethane has 2 carbon atoms. And we say that carbon, to be complete, must have all its 4 carbon, sorry, it must have all its 4 bonds. So it has already used 1 bond, so it will have 1 other bond, another bond, another bond, like that. So that means we'll have hydrogen here, hydrogen there, hydrogen here, hydrogen here, hydrogen here, and then hydrogen there. So you realize that this first carbon has 3 hydrogens. And then this other carbon also has what? 3 hydrogens. So this is the same molecular formula as someone who would write C2H6. You get the point?
Yeah, so they are the same.
Yeah, it's the same. It's just that this one is a compressed formula, while this one is more expanded than this one here. So as well as we call this a structural formula, we call these two the molecular formula, because they are showing you what is composed in the what? In the molecule without spreading it out. So they are the same.
Okay, now.
Okay, thank you. Okay, those asking about the lesson, when today's lesson is posted, that same link that they will post for today's lesson can take you back to the lesson that you had previously. Or even the link that you're using is a math lessons, if they are being posted, I don't know, or any other lesson that you're having. It's the same YouTube channel. It's help lessons. I'm not very sure of what comes after that, but at least it has help lessons in it. So you can go on YouTube and look for that, and you'll be able to get sorted. Okay, so going back to what we were sharing. Like I said, when you look at the physical properties of something, you should be able to look at the physical properties as well. So in this case, the chemical properties that we have, one of them is combustion. Who has an idea on what combustion is? Yes, Desire? Patricia?
Combustion is a chemical reaction which takes place between oxygen and an element or compound, giving products which are mainly oxides, but it's not accompanied by a flame.
Okay, thank you. Mirinda? The host, did you meet these people? How come when I call their names, they don't unmute? Is it that they can't unmute themselves? What's going on?
I didn't mute.
Combustion is a chemical reaction between an element and oxygen to give an oxide.
Okay, very good. So when we are looking at combustion, basically it's a reaction between that given compound and oxygen. So when you're looking at combustion, I think most people are posting burning. So it involves burning, but in this case, the reaction, because we know that the main gas that supports burning is oxygen. So in this case, you're reacting something else with what? With oxygen, or burning something in oxygen, without necessarily having to produce a flame. And then we have halogenation. Anyone who has an idea on what halogenation is? Okay, thank you for posting the YouTube video link. I hope people can now access it. Okay, anyone with an idea on what halogenation is? Yes, Jessica?
Halogenation is a type of chemical reaction that involves the replacement of a halogen atom with another substance.
Okay, thank you. Hannah? Please, Saint and Patricia, try to ask people to unmute if you muted them, because otherwise I can't be unmuting them and then.
Teacher,
Yes, please.
can you hear me? Halogenation is of an alkane produces a hydrocarbon, in which one or more halogen atoms are substituted for hydrogen atoms.
Can you repeat that again?
Halogenation of an alkane produces a hydrocarbon in which one or more halogen atoms have been substituted for hydrogen atoms.
Okay, thank you. So when we are looking at halogenation, if you looked at periodic table, you should remember that group 7 elements are also called halogens. So anyone to tell me some of the group 7 elements that we know? You can post in a chat or you raise your hand and tell us. Yes, Samsung. But why don't you use your real names instead of using your phone names?
Teacher, I just remember fluorine.
Fluorine. Another one?
Chlorine.
Chlorine.
Another one? Iodine.
Bromine. Iodine.
Bromide.
Okay, can we only talk when we've raised our hands? Because otherwise we are becoming a window market.
Fluorine.
Astatine.
Chlorine and fluorine.
Okay, so we have fluorine, chlorine, iodine, and then what? Bromine. So those are what we call halogens. So the term halogenation comes from the word halogens. So when we add the word ation, that means you're adding a halogen to a carbon compound so that you form what? Basically, a compound that has a halogen in it. And then, of course, since we said when we have methane, for example, is bonded to 4 carbon atoms, if we add chlorine to it or fluorine to it under UV light, ultraviolet light, that means this carbon, these hydrogen atoms are going to be replaced by the what? By the chlorine atoms. And then you'll have 4 there, and then 2 here, 2 hydrogens. So basically, you'll have something like this. You'll have the chlorine replace the hydrogens in the what? Where the hydrogen was initially. And then, of course, you'll have hydrogen removed from the carbon, and then it will give you hydrogen gas. So basically, halogenation is that combination between an alkane and a halogen to give you a compound of a halogen the other side, and then the what? The hydrogen gas. So basically, that is what you'll have in halogenation. And of course, you'll look at those things in more details for some of you that will do chemistry at A level, but our O level chemistry is a bit limited to some things. Yes, Wandera.
Okay, madam, may you please pardon and give a very brief explanation about halogenation?
Okay, I've said when we are looking at halogenation, we have first of all to understand what are the halogens we are looking at. And I've said halogens, for some of us that had covered periodic table, halogens, we have fluorine, we have chlorine, we have iodine, and then we also have bromine. These are group 7 elements. But their other name is also called what? Halogens. So that means if I am dealing with that term halogenation, that means I am getting that halogen, adding it to something else to produce another compound. Because of course, if you're adding 2 components, you expect to get a product.
Yes.
Are we together?
Yes.
So at that point, if I had, for example, methane, which is C4H,
yes,
plus 1 halogen here, it may be fluorine, it may be chlorine, it may be iodine, it may be bromine, any that you choose to use. So in this case, if I use chlorine, of course, I'm just using this as an example, but at this level, you don't really need these equations. So the condition for this reaction to take place, like for example, some equations in chemistry where we need heat. In this case, we need a condition of ultraviolet what? Light for it to take place. So when this ultraviolet light is available, you will have the chlorine replace the what? The hydrogens in this case. Of course, it's we have what we call the slow reaction and then the fast step reaction. So it will go on in steps. While removing this hydrogen here, the chlorine will keep on adding itself there until you have it replace all the hydrogens and you have carbon and bonded to 4 chlorines. That means in this case, you're going to have, let me just use a whiteboard here. You remember initially I had something of this sort with the methane. So that means when the hydrogen atoms are replaced, that means still 4 halogens will have to replace those hydrogen atoms. So if I have plus chlorine under UV light, that means I'm going to have chlorine here, chlorine there, and then chlorine here. Plus what? Plus hydrogen gas this side. But of course, I need to balance the equation, and you'll study those things on a later date. So that means at this point, this process is called halogenation because the chlorine has replaced the hydrogen atoms in the carbon chain. Akram, are we now together? Even those other people that had it understood that point.
Yes, madam.
Okay, thank you.
Welcome, madam.
Okay, so we move on. So we have an experiment on the combustion of an alkane. I hope all of us can see the screen. So when we are dealing with an alkane, an experiment to show the combustion of an alkane, we use a candle because a candle is made up of an alkane. What is the name of that alkane that we find in the candle? Who has an idea on the name of that alkane? Okay, thank you, Shani and Joyce. But in a candle, we find methane. So that means when we are dealing with combustion of a candle, we are basically testing the combustion of what? Of methane. And we say combustion is the reaction of a compound in oxygen. So basically you will have methane burning, and of course, as it burns, we realize that there are some gases that are going to be given off. And that is why in our next container here, you realize that we have anhydrous copper 2 sulfate. Who can remind me what anhydrous copper 2 sulfate tests for? Which chemical substance do we test its presence using anhydrous copper 2 sulfate? Sorry?
H2O.
It's called water, not H2O. Thank you. So we have water. So that means we expect that in our experiment, we are going to produce water somewhere because we have anhydrous copper 2 sulfate. And then, of course, we have the cold water. Who knows what the importance of that cold water is? Miranda, I hope your background is now clear because the last time it was very noisy. You can unmute and tell us. Okay, Shannon, since Miranda can't unmute.
I think it's to cool down the vapor.
Okay, very good. And I've seen some people in the chat are suggesting to condense. Yes. So as the vapor comes in, we expect it to cool. So in that case, you'll have a cold water bath outside the what? The trough that has the copper 2 sulfate. So in that case, you realize that the vapor will cool and what will the color of the anhydrous copper 2 sulfate be if water is present in that case?
Blue.
Okay, very good. So it will turn from white to blue to show us that the water was actually there. Okay, that is very brilliant. Then, of course, that's not all. You realize that there is a delivery tube connecting us to another tube, and that tube contains lime water. What does lime water test for?
Carbon dioxide.
Very good. It tests for carbon dioxide gas. So what observation will we have if carbon dioxide gas is present in this experiment? Kim? Okay, let's have Will Faith.
Madam, I think the water turns milky.
Okay, very good. So the lime water turns milky to show that carbon dioxide is actually present in that experiment. So in some cases, if we are not in the lab, we expect that instead of using lime water, which name can you use? What is the chemical name for lime water? Hannah? Let's hear from Bridget. Okay, Angel Rose, that's true. The lime water can also be called calcium hydroxide. So in that case, we are using calcium hydroxide. Instead of using the word milky, we say the color solution turned to a white precipitate. So you need to take note of some of those observations. So that means when a candle burns, which products do we expect do we expect that candle to give off? Which two products according to our experiment? Yes, Saint?
I think water and carbon dioxide.
Very good. So we'll give off water and carbon dioxide. So basically, that means in this case, we have methane reacting with oxygen to give us carbon dioxide and water. So this was just an experiment to show us that when we get a product that is an alkane, for example, a candle, which contains methane, and we burn it or we burn it in oxygen, you realize it's going to give us water and carbon dioxide. And please take note of some of those tests. So if we've not used anhydrous copper 2 sulfate, which other chemical compound can we use to test for the presence of water in the lab? Yes, Aaron?
Anhydrous cobalt 2 chloride.
Very good. So we can use anhydrous cobalt 2 chloride or cobalt 2 chloride paper. And what observation do we expect to get? Bridget Jones? Sorry? Yes, Aaron.
The solid changes from blue to pink.
Very good. So it turns from blue to pink. So when you use cobalt paper, you expect that it will turn from blue to pink. Please, it is always important for you to note the previous color and then the initial color. So don't just say it turns pink. It's important that you state the previous color to the new color that is changing to. That's why it's important to know both colors as they occur. I can see someone wrote sodium chloride. We didn't say sodium chloride, we said cobalt 2 chloride paper or anhydrous cobalt 2 chloride. Okay, are we all together up to that point so far? Okay, thank you for that feedback. So we've said here the major two elements that make up the hydrocarbons. Who can tell us those two major elements? Will Faith?
Madam, I'm sorry. I just wanted to get to know the SP of anhydrous cobalt, but I've gotten it.
Okay. Okay, thank you, Jessica. So we have carbon and hydrogen. Nairobi, is that your name or? Please, if you're not talking, keep your mic muted because it keeps sending feedback, which is not really sounding nice in my ears. Okay, so there are two major elements that make up a hydrocarbon. We have carbon and hydrogen. So it's important to take note of that. And then what happened to the anhydrous copper 2 sulfate solution and why? Who can tell us what happened and why? Yes, Favor?
Can you hear me?
Yeah, please go ahead.
Yeah, it turned blue because there was presence of water.
It turned blue due to the presence of water. Okay, thank you.
You're welcome.
And then we've mentioned this, what other substance can be used apart from anhydrous copper 2 sulfate and set the expected observation. And we've said you can use anhydrous cobalt 2 chloride, which turns from blue to pink. And then what happened to the calcium hydroxide solution? And then give a reason for your answer. We've also mentioned that one. Where lime water was used, we can call it calcium hydroxide. And when they use calcium hydroxide, please, you don't say it turned milky. You say the colorless solution turned to a white precipitate. And of course, because of the presence of carbon dioxide, that's why it turns to that. Okay, and then the equation for the reaction, I've said we have the reaction between methane, the reaction between that took place for the equation for the reaction that took place for this question here. We have calcium hydroxide plus carbon dioxide to give us calcium carbonate and then water. But of course, our experiment, like I said, you'll have methane, you'll have methane plus oxygen to give you carbon dioxide plus water. So that is what you get during that experiment. Methane plus oxygen giving you carbon dioxide plus water. Please, we may not have the whole time to copy. You may have to just take a screenshot and then watch the video later and then take notes. Otherwise, if we wait for everyone to copy, we may spend all the time copying instead of looking at something else. So you may need to take a screenshot, then you can revisit your phone or PC and then copy down word per word. But for now, you can note down a few things that are important and then we can move. So we said, of course, the use of the ice cold water is to cool the what? The vapor. So alkane and methane belong to the same homologous series. So when you write the, like I've written for us the equation that that occurs during the experiment. So I'm going to request us to stretch for just 5 minutes. So in 5 minutes time, we should be back and then we can look at crude oil. So stretch your legs a little. Those who have questions, I can take them. Patricia, your hand is up.
Yes, madam. The part for the experiment, they ask you to describe like how to set up the apparatus for the experiment. How do you do it?
Patricia, I'll leave that one for you. In the next lesson, you tell us what happens and then I can guide you at that point. Is that okay?
Yes.
Yeah, so find out. Then in the next lesson, as we begin, you remind me and then you tell us what you found out. Or you can even inbox me what you have come up with and then we can see how to better read. No, Shani, I'm not looking at chemical formula at this point. I don't want to confuse people. You can look that up for yourself, for your own personal advancement. But for the rest of the class, they may bring in questions which I may not have answers to for now. So you can look up the formula yourself and you can write it and have it for your academic value. Mustafa, why do you want to share your video? No, we are not done with the lesson. I said I've given us 5 minutes to stretch. Yeah, because I don't believe in having a marathon class and people are no longer understanding what I'm teaching. So just stretch a bit. You can even go for a short call. Don't go for a long call because it may take more than 5 minutes. So just go for a short call, walk around, greet your siblings a little, something like that. Otherwise, the lesson is still on. So we have about maybe 2 minutes or 3 minutes, and then we resume. Have I enjoyed the break that she's even writing on the screen?
Thank you.
Okay, so we are moving into crude oil. I know most of us have heard about crude oil. Please tell me something you know about crude oil. Please, Muine, behave, stop writing on the screen. Anyone who has an idea on what crude oil is? Yes, Joy? Joy, please unmute and tell us.
Crude oil is a mixture of hydrocarbons that exists in liquid phase in natural underground reservoirs.
Okay, thank you. I presume that word is reservoirs, if I'm not mistaken.
Oh,
yeah, but
okay.
Thank you. That is good. Patricia?
Crude oil is a mixture of different hydrocarbons, organic and inorganic compounds that vary according to the source.
That vary according to
the source.
Okay. Where do we find crude oil? Okay, let's first hear from Desire, maybe, before I hear from where we can find crude oil.
Crude oil is obtained from ancient marine animals and plants that existed long time ago. Madam, can you hear me?
I was asking, where can we find crude oil?
Madam, I was saying that it's obtained from ancient marine animals and plants.
Okay, where do we find those?
Down underwater body.
Okay, thank you. Akram? Akram, please unmute and tell us.
Underground.
Underground, okay, James?
Oil wells.
Oil wells, okay, thank you. Stacy?
It is found from anaerobic decomposition of the sea plants and animals.
Okay, thank you. Okay, so when we are looking at crude oil, you need to understand where it comes from. So you realize that it is as a result of the decay of organic substances. And organic substances, those are things that can easily decompose. Maybe animals, plants, and these things have decayed for millions and millions of years. And of course, they're deposited either underground or in between rocks beneath the water surfaces. So you find them in those places that are rather deeper where they can easily be what? Mined or extracted by mining. So what is the color of crude oil? Who has a clue? Please, let's use the chat for sensible things, at least for now, because the break is already done. Okay, Joy, I can see you said black, good. Kim, black, good. Let's hear from James and then Patricia.
It's either black or dark brown.
Okay, Brett.
I think it's light yellow to black.
Okay, good. So you realize that it has that variation of brown, black, or black. So, so crude oil is thick, dark brown, or a black liquid. And I know at least some of us have seen the documentaries of how those things are made. So what is the other name of crude oil? Who knows the other name of crude oil? Yes, Patricia.
I think fossil oil.
Okay, fossil oil. Okay, I'm seeing some answers here. Rock oil, fossil fuel, petroleum oil, petroleum. Okay, so the other name of crude oil is petroleum. I know most people confuse petrol with petroleum, but those are two different things. Petroleum is where we get petrol from, so they are totally different. So the other name for crude oil is petroleum as well. Thank you for your contributions, all of you. And then why is crude oil known as a fossil fuel? Who can tell us? Yes, Desire? Desire, you can unmute and tell us.
Madam,
Mm-hmm.
it's known as a fossil fuel because fossil fuels are got from ancient plants and animals, and what petroleum is also got from the ancient plants and animals.
Okay, that is good. Okay. Thank you. Joy, do you have a different submission?
Yeah.
Mm-hmm.
It was formed from remains of ancient marine organisms.
Okay, good. But it's not only marine organisms, even plants, animals that are not marine.
Okay.
Okay, let's listen from Lena. I don't know if that's a pronunciation of your name.
Because it's a mixture of hydrocarbons.
Okay. Okay. So basically the reason why it's called a fossil fuel is the fact that there is decay over millions of years of these organic substances. Okay, so it is formed from remains of living organisms that lived many million years ago. So that is why when you are looking at renewable and non-renewable fuels, you realize that crude oil falls in one of those falls under one of those fuels. Which fuels does it fall under? Renewable or non-renewable? You can post your answers in the chat. Someone is saying renewable, another non-renewable, another non-renewable. So we find it under non-renewable fuels. Reason being, if we, for example, the oil they discovered in Uganda, if they mined that oil over and over and over again, and it was all depleted, that means when it gets done, it will take us most several years for us to regain that oil, or even not to gain it back, or even generations after that may come in may not even know that there was oil one time at that place. So it takes several years for it to for you to obtain it. So it's a non-renewable fuel. Okay, so by what process is crude oil formed? Who can tell us the process by which crude oil is formed? Yes, Saibo. Is it? Saibo, you can unmute and tell us. Okay, let's hear from Joshua.
Hello.
Yes, we are hearing you.
May I say crude oil is formed by drilling. Don't know if I've said how it's mined, but that's what I think. Drilling.
What do you mean by drilling?
Like, okay, where certain like machines are put like directly into the ground, and the people who are under like the ground are the ones who direct like the machine, like where to suck the crude oil from.
But remember, the question is asking us how it's formed, not how we obtain it. I don't know if you took note of that. Samsa?
Teacher.
Mm-hmm.
I think fossilization.
Okay, what is fossilization?
Like, well, I think it's a way how organic matter changes into fossils, if I'm not mistaken. That's what I think.
Okay, in the chat, I can see a lot of decompositions. So we've said it's formed after remains of living organisms that lived many million years ago. So we expect those things really decomposed or they decayed. So we don't expect them to have magically formed, but there is that decomposition over a very long period of time. So really it's decay or decomposition. So for everyone who tried, thank you. So are there people taking screenshots so I can move to the next slide? Okay, and are we all together up to that point? At least we've understood how crude oil is obtained, what its color is, and why it's called a fossil fuel. Okay, good. Thanks for the feedback. So how is crude oil purified? That is what we are going to look at now. Anyone who has an idea and can tell us what they think? Yes, Joy?
Firstly, you remove the sulfur. then heat the oil. After heating, then vaporize it. Then after, introduce into a fractionating column. It is separated at the end, and the process is fractional distillation.
Okay, thank you. And I can see most people here are giving me some people are giving me fractional distillation. But I want to hear more of that explanation that you're talking about. Okay, so when we are looking at the description of how crude oil is separated into its pure components, we've all understood that we use fractional distillation, but I want someone to take us through how does that fractional distillation occur? Desire, do you want to say something?
Yes, madam. The reason why we use the fractional distillation is because, for example, when you are separating the crude oil from water, the two have different boiling points.
Okay.
So we shall need a heating. We shall need heat. Then also we shall need the crude oil and the water. Madam?
Yes, I'm hearing you.
So what will happen is that we shall increase the temperature gradually until a constant temperature is attained. So, so the one which will have the highest temperature is the one which will be separated, highest boiling point.
Okay, good try. Thank you. Let's hear from James.
This crude oil is heated and its components are separated based on their different boiling points. The various fractions include gasoline, diesel, and others are collected at different temperature ranges. Additional refining steps such as cracking and treating may follow to further purify and enhance specific properties for the refined product.
Okay, that is good. Thank you, James. Okay, so in brief terms, we all know what the principle of fractional distillation. You're obtaining miscible liquids with differences in their boiling point. So in this case, like you see petroleum or crude oil, you realize that it has different components in it. And those different components have different boiling points. So that means the ones with low boiling points will be collected off first, and then the rest will flow into the different trays at which they'll also be distilled off. So what are some of the components we find in crude oil? You can list them in the chart. What are some of the components we find in crude oil before we go into the separation? Diesel, good. Please, for this case, post in the chat where everyone can see it. Glycerin, petrol, good. Please post for everyone so that at least everyone can be able to see what you're posting. Don't do a direct message. Natural gas, paraffin, good. Kerosene, good. I want us to really observe the organic components for now. Because remember, we are looking at carbon in life, which involves organic components. So even in the separation, I expect that our answers are organic related answers. So you have petrol, paraffin, natural gas. So when you say kerosene, you don't say paraffin. You at least mention one of that too. Okay, at least all of us have a clue. This is good. I don't know if people are Xeroxing from the internet or from textbooks, but this is a good thing. The activeness, at least the urge to show that you want to say something, it's good. Then why is the method mentioned above used? Of course, we've said the difference in boiling points. Then identify the different fractions of crude oil and their boiling points. This is what you are going to look at. What are the uses in daily life? So my picture may not be very clear because of the resolution, but I'm going to read for us. So please just take note of what I am reading. So of course, we've said we pass the crude oil under a furnace. A furnace, that means it has an expected temperature that it should have for it to heat these different components to come out. And that furnace may be about 450 degrees Celsius, whichever hot it is. Okay, so our first collection is the natural gas. That is why you can see something like a gas cylinder this side. So as you look at these diagrams, they should be able to direct you to the different uses of these components, because that will be my next question after telling you the different components that are given off at the different stages. So we have natural gas being given off first because it has the lowest boiling point in petrol. Of course, these are different trays. And of course, we know that gases have lower boiling point compared to liquids and then solids. Because you realize that we say these alkanes exist in terms of gases, liquids, and then solids. So we realize that the gases have a lower boiling point, followed by liquids. Then the solids that have a higher boiling point are the ones that settle at the bottom trays. So in this case, our first one is natural gas. And then our next one is petrol, or what you can call gasoline. And then we also have naphtha, which is our next fraction. Then we have paraffin. Then we have diesel. Then we have fuel oil. Then we have lubricating oil. And then we have the bitumen. So I'll do that again. We have natural gas being given off first, followed by petrol or gasoline. Then we have naphtha. Then we have paraffin or kerosene. Then we have a person complaining about the letters. That's why I'm reading. I said the resolution is not so good for the diagram. So listen as I read them for you. So we have paraffin here. Then we have diesel. Then we have fuel oil. Then we have lubricating oil. Then we have bitumen and waxes at this point. So the first one, like I said, we have natural gas. I'm repeating for the last time for those that weren't taking notes. We have natural gas. Then the next one, we have petrol or gasoline. Then we have naphtha. Then we have paraffin or kerosene. Please stick to the ones whose spellings you know so that you don't write wrong spellings. Then we have diesel. Then we have fuel oil. Then we also have lubricating oil and waxes. Then we have bitumen as the last fraction. The spelling of the third one I said is naphtha. N-A-P-H-T-H-A. Okay, so we are going to look at the different. I'm going to task us to go and find out the temperatures at which those different gases are obtained. Yes, Sarah, your hand is up. Sarah?
What was the seventh one?
The seventh one, I said lubricating oil and waxes.
Okay.
Lubricating oil and waxes. Okay, so what is the use of natural gas? These diagrams should guide you a little on what is there. Yes, Akram?
Okay. Natural gas is used in gas cookers.
Okay, good. Used in gas cylinders, gas cookers. Very good. And then petrol or gasoline. Yes, Tess. Casey? Okay, Patricia.
It's used to run car engines.
Okay, it's used in cars or to run car engines. Very good. And then naphtha. Bridget.
Okay, teacher. It's used for diluting heavy crude oil.
Used for diluting heavy crude oil. Good. Any other use of naphtha? Okay, then paraffin. Anyone with a clue on what we use paraffin for? Yes, Ian? Patricia? Ian, I didn't hear anything from you.
Okay, I'm seeing an airplane there, so I think it's used as the fuel, like for running those planes, aircraft.
Okay, it can be used in aircrafts. Makai?
Used in lamps.
Okay, good, used in lamps. And then someone is saying in stoves. Those are good answers, thank you. And then we move on to diesel. Akram? Please, when we ask you to unmute, kindly unmute, so that we save time. Akram?
Diesel is used in car batteries.
Used in car batteries, good. Used in car engines, good. Desire?
It is used on petrol stations and it's used by motorcycles and cars and lorries.
Okay, it's used to run engines of different means of
Vehicles.
transport. Okay, then we move to fuel oil. What is fuel oil used for? Unless this diagram should be able to direct us on what we are supposed to answer. Yes, Bridget.
It's used for industrial heating.
Industrial heating. Okay, Rebecca.
It is used in both engines.
Used in both engines, okay. Infinix. James. Okay, and then lubricating oil and waxes. Bridget.
It is used in lubricating
Okay,
machine.
good. Patricia.
Had the same.
Okay. James.
It is used in road construction.
Which one?
Bitumen.
Here we are still on lubricating oil and waxes. But thank you, yeah, bitumen is used for in road construction. That's that most of us see. Okay, then the waxes also and the lubricating oil. We see that most of the jellies as a result of those waxes and the lubricating oil. Okay, so we'll continue. So you see the reason why we mute you people. When we unmute you, your microphones are always very loud, disrupting the lesson and the recording. So the people that come back to watch these videos just hear the noise in the background and they can't hear what is being told. So let's learn the discipline of being in quiet places when we are unmuted. Yeah, and I don't know, when I choose you, you put your hand down and then your microphone just keeps sending feedback. You have a question or you're giving us an answer? Okay, let's proceed. So we have the different fractions of crude oil and their uses. Of course, these are some of the uses we've already mentioned. So this is just a summary. So you can take a screenshot and go back and add more uses or even write them down so that you can have them for future reference. So we have natural gas, which has propane and butane, used as a fuel for cooking and lighting. Then we have petrol for motor and aviation fuel. Then we have paraffin or kerosene used for lighting and heating and a major fuel in jet engines. Then we have gas oil used to make petrol, or the one you call fuel oil. Then diesel used for diesel engines of trains, lorries, and tractors. Then lubricating oil used in lubrication in machine parts. Then waxes and bitumen in production of Vaseline, lenses, candles, also tar used on roads and runway surfaces. So most of us have seen that black tar they use on tarmac roads. It's as a result of the bitumen that is obtained during the mining of, during the fractional distillation of what? Of petroleum. And like we said, these fractions do not come out as expected, especially petrol, and yet it is required for car engines. So in that case, you realize that you're going to have to apply what we call cracking. And when you crack these fractions, like the way you hear the word crack, what does crack mean? Anyone with an idea on what the word crack means? Yes, Desire. Desire, you can unmute and tell us.
Madam, crack means like, for example, when before something breaking, it first forms something like lines or something like, how can I explain it? Like before it initially breaks, it forms like lines in it cracks.
Okay. It's more like creating a breakage between something. So it's the same thing that happens for these alkanes that are obtained during fractional distillation. So let me get someone to read for us these statements as we wind up. This is going to be our last slide. And then in our next lesson, you can go and find out about natural gas. That's where we'll begin from in our next lesson. Yes, Bridget.
Okay, the heading cracking. Fractional distillation of crude oil yields only about 20% of petrol, yet there is an increase on its demand, hence cracking of gas oil. Cracking is the process of breaking down the long chain hydrocarbons into shorter chain molecules. Large molecules of oils can be broken down into small molecules of petrol and gases by cracking. Thank you.
Okay, thank you so much. So, like we say, fractional distillation will not give you the exact quality of the petrol that you need. So in that case, you're going to apply cracking to gas oil because we say gas oil is one of the components that can avail for us petrol. So in that case, you'll apply the breaking of gas oil because remember, since gas oil is on a lower trade, that means it has more carbon atoms than petrol, which is higher. So in that case, you realize that we'll break those long chains into shorter ones, which is referred to as what? Cracking. And we have two types of cracking. We have catalytic cracking and then thermal cracking. And like you hear the words catalytic comes from the word catalyst. So that means in that type of cracking, you apply a catalyst to break down that long chain. And for the thermal, you can hear the word thermal. That means you apply heat to break that what? That long chain into shorter chains. Then the large molecules of oil can be broken down into smaller molecules of petrol and gases by cracking. So those are some of the important things that you need to know. So thank you all for being an active class. Read about natural gases and remember to rewatch these videos and so that you can come up with organized notes as you write them. All right, thank you all. Have a lovely weekend. See you next week. And please next week log in early so that you don't have to ask, Madam, where are we? Where have we reached? All those questions. And then watch the videos as well so that if you have any questions, we can always review and see how to answer those questions. Okay, Wandera, you want to pray for us? Please go ahead.
Okay, let's humble ourselves and we pray. Oh Lord, we want to thank you for this day. We want to thank you for the madam you've granted to us. We want to thank you for the knowledge you've brought to us today. May you make us remember this every time that we come to this. We thank you for our teacher and everything. Thank you very much. Amen.
Amen. Thank you so much, Wandera. Okay, the rest of us have a lovely day.
Amen.
Amen.